Question 3 is about extracting some information from slope fields, from direction fields of differential equations. Part A, which of these equations have equilibrium solutions? So let us try to plot this equilibrium solution. So an equilibrium solution looks like arrows that are arranged along a straight line, so all the arrows point exactly to the right. So this is an equilibrium solution, this is an equilibrium solution, this is an equilibrium, and this is an equilibrium solution. So the other two vector fields do not have equilibrium solutions. So the right answer is A, B, C, and E. Part B, which of these equations are autonomous? So autonomous equations are those that are invariant on the horizontal translation. So imagine if you move the whole thing to the right or to the left, then you get the same thing. Or what you can see is that if you kind of look at all the arrows for some specific value of y, then all these arrows should point in exactly the same direction. Or all these arrows should point in exactly the same direction. All these arrows point in exactly the same direction. So only one of these differential equations is autonomous. It is equation E. Maybe just for comparison, so if say you tried the same thing for, I don't know, A, then you see that I'm trying to follow these arrows for a specific value of y, but the arrows are different, or I don't know, here. Again, so only these arrows in this highlighted portion are different. Arrows in this highlighted portion are different, while for equation E, all these arrows in these highlighted portions are the same. So which means that it is autonomous. All right, so the correct answer is E. Now the third question is, given that at least 3 of these differential equations are separable, which ones are separable? Well, for starters, an autonomous differential equation is separable, so E is definitely separable. The next thing that we need to do is, if you recall what we learned in tutorial 2, there was this necessary condition for the direction field to be the direction field of a separable differential equation. It is not sufficient, but it is necessary, right? So it tells us that if we have a separable differential equation, then the set of zeros of the right-hand side has the structure of some horizontal lines and some vertical lines, right? So let us see. So what is the set of zeros of the right-hand side is in each of these cases, right? So let me try to trace the set of zeros of the right-hand side. So A, these are zeros of the right-hand side. So zeros of the right-hand side means that we should look at all points where the arrow is horizontal. So here the arrow is horizontal, and also here the arrows are horizontal. In this case, we have one horizontal line, one vertical line, and one slant line. So since this is not the union of vertical and horizontal lines only, it means that A is definitely not a separable differential equation. Now let us look at B. So in B we have, this is zeros of the right hand side, and we have a vertical straight line, so which means that B may be. So it has the right structure, so it may or may not be separable. C, so let's look at C. Here, that's all. I think in B there is one more. Okay. So in B, the set of zeros of the right hand side is the union of two vertical and one horizontal lines. In C, it is the union of a vertical and a horizontal line, but in both cases, it is consistent with differential equation being separable. So both B and C may be. Now let us look at D. So in D, if you uh, stare at it carefully, you will notice that these are, sorry, yeah, these are zeros of the right hand side. So we are looking for horizontal arrows, and the set of zeros of the right hand side for Z has the structure of two slant lines. So they are not vertical or horizontal, so no. And for F, it is a bit tricky, but in F, you can imagine that there is kind of like a circular shape, because outside this shape, arrows point kind of upward, inside kind of downward. So which means that on this circular shape, the arrows point exactly horizontally. So the set of zeros of the right hand side is something like a circle. Well, in fact, it is a circle, but it is somewhat like a circle, but it is definitely not the union of horizontal and vertical lines. So which means that that's not it. So what we see is that A, D, and F are not it. And given that three of these six differential equations are separable, we conclude that these separable ones are B, C, and E. Question 3. Given that at least two of the six differential equations are linear homogeneous, which ones are linear homogeneous? Right, so what is a linear homogeneous equation? So let me remind you. So a linear homogeneous equation is an equation of the form y prime equals p of t times y. So if it is linear, if it were linear non-homogeneous, then we would have plus something else like plus g of t. But if we don't have plus g of t, then it is linear homogeneous. So what is special about linear homogeneous? So notice that y equals 0 is a solution. So another special property is that if we have a solution, say y of t is a solution, then if we multiply it by any constant, I don't know, like 3 or minus 1.5 y, then we also get a solution. So all solutions are proportional to each other. So which of these vector fields have these properties that y, the zero, the constant 0 is a solution, and solutions are proportional to each other? But well, actually just two of them have the property that constant 0 is a solution. These are B and C. And given that at least two of the six differential equations are linear homogeneous, it means that it has to be B and C. But at the same time, if you look at solutions, then you will see that, yeah, that the solutions are kind of proportional to each other for both B and C. So different solutions, they are constant multiples of each other. So that's a property of linear homogeneous differential equations. So here we have direction fields of the same differential equations. Which of these direction fields is the direction field of the differential equation y prime equals t squared plus y squared minus 2? Well, let's try to reason logically. Let us think for which values of t and y the right hand side of this differential equation is positive, and for which values is negative. So notice that y prime is positive if t squared plus y squared is bigger than 2, and y prime is negative if t squared plus y squared, is less than 2. Well, now, what does it look like? The curve given by the equation t squared plus y squared is exactly 2 is a circle of radius square root 2 centered at the origin. Now, we need to look for the direction field where inside this circle all the arrows point downwards, and outside this circle all the arrows point upwards. Do we have something like this? And then if you look at these six direction fields, you will notice that D is the right one. And because here we have the circle, inside the circle arrows point downwards, outside the circle arrows point upward. So the correct answer is F.